All right, welcome back to the continuation of the session on ionosphere and space weather. I'm Erin Lynch, and I think let's welcome our first speaker for this session, Victoriya Forsythe from NRL, to give an invited talk on Anchor.
Hi everyone, I'm Victoriya Forsythe from Naval Research Laboratory, where we're working on developing a new data assimilation model for the ionosphere. It calls Anchor. Anchor is relatively young. I've been working on it for 2 years, and I think it has a bright future. So the approach for Anchor is that we don't need to have a lot of points in our data simulation to represent the vertical structure of the ionosphere. All we need is only 12 parameters, because the very realistic electron density profile of the ionosphere can be described with only 12 numbers. We have 3 numbers that describe the electron density in F2 region, F1 region, and E region. Then we need 3 numbers for the height of those levels, of those layers, HMF2, HMF1, and HME. Plus, we need 2 numbers to describe the thickness of the F2 layer, thickness of the top side, thickness of the bottom side, and so on. So we don't do assimilation on all of the 12 parameters. We just focus on 5 parameters, which are NMF2, HMF2, the thicknesses for the F2 layer, and the density in the E region. For the background, we used a Pi-IRI model. It's a full rewrite of the classical international reference ionosphere model. And it's not just a rewrite, it's full rethink of how this model works, because classical IRI model was developed, in the early days when it's a punch card approach to programming. For example, you would find the electron density at one geographical location. Then in order to move to another location, you'll do this whole process of generating your functions and opening the coefficient file and determine the density. And then if you need to change your time or your position, you just repeat this process again and again and again. So this all was rewritten so that the electron density are being evaluated simultaneously on the whole geomagnetic grid. And this takes only 3 seconds to determine electron density for the entire day for a pretty high resolution global grid. Anyway, it was just like advertisement. The code is publicly available on GitHub. Just keep install Pi-IRI. For the covariance, we're using kind of like ensemble of the different time frames for a particular day, but we do it in more natural for the ionosphere coordinate system. We use magnetic local time, quasi-dipole latitude coordinate frame. And this is an example of how the covariance looks like for the NMF2 parameter. So the points are shown like a reference points and how the correlation drops around those reference points. What I like about this covariance is that it actually has some ionospheric horizontal structure information in it. For example, close to the 12 MLT, magnetic noon, we have those secondary peaks. Oh yeah, just up here. It's impossible. And those are these secondary correlation peaks that show the structure of the equatorial ionospheric anomaly. We currently can ingest 3 data types: cosmic 2 data, well, any or commercial satellite data, so any radio occultation hot tech files, plus ground-based GPS data and ionozone data. So for the cosmic 2, what we do is that we don't ingest those raw tech measurements. We first massage the data as much as we can to extract those anchor points. So we, from the Abel inverted profile, we extract HMF2 and NMF2, and the thicknesses of top and bottom sides, we find the thicknesses from fitting the Epstein functions. as shown with red and blue here. And we also extract the density of the E region. So then for each profile, we collect the position of our NMF2 and HMF2 and the position where the electron density in E region was observed, because since it's not a vertical profile, but profile along the tangent point, those positions are different. So then we record those positions, we do the coordinate transformation to the anchor MLT quasi-dipole latitude system. And on your left, you can see from 1 hour how those anchor points are being distributed. All right, then the assimilation itself. So here's the results of the OSIS study, where we use SEMI3 to generate synthetic data, but then we ingest it into PyRI background. So this is an example for NMF2. We start with NMF2 background. Then, since we know the truth, we generate the data according to the truth. And then we ingest those point measurements into the background to produce the analysis and percent differences, basically by how much the background was changed to match the data better. So we use the Kalman filter equation, and we do it only in this two-dimensional coordinate frame. So for each parameter, we use those maps. Okay, and we do it simultaneously for all 5 parameters. So all of the parameters that describe the electron density profile are being corrected. Here is the results of OSIS study again. So we're here looking at root mean square errors, and the black line shows where we start from. So it's root mean square errors of the background in comparison to the truth. And the yellow line is basically how low can we get in our root mean square errors. And again, in most of the cases, we reduce the errors by half at least. The results were published in Space Weather Journal. So next I'll talk about ingestion of ground-based STEC data, because it's slightly different from the classical data assimilation techniques such as ionospheric density, like IDA4D type of data assimilation. So in this approach, what's different is that we concentrate only on NMF2 parameter. Why? Well, because slant total electron content measurement is an integral along the line of sight, right? So it's it cannot be localized to a particular region. So if we, for example, observe a tag that is 20% greater than the background, how do we know what parameter to change, right, to match that observed tag? It can be that the profile can be thicker, it can be that NMF2 is larger, or it can be both, so it can be an increase in all of the parameters. So this simple example can illustrate this. So yellow profile is the truth. Then we calculate the vertical tag according to this truth. And we start with the blue background. And then we ingest this vertical tag in this classical sense, like IDA4D does it. And we produce the analysis. So analysis is shown with red. So you see how the NMF2 improved. It increased according to the truth, but the height of the profile stayed at the same place. And now if we put it into numbers, let's look how all of the parameters changed in that profile. So the picture on the right shows those bars. So the blue bars are the background parameters, so what we start with. And the red ones are the analysis. So if the red bar is smaller than the blue bar, it means, yes, good, we're improving. The first thing is vertical tag. And yeah, we ingest vertical tag, we have to improve here, so it's all good. The NMF2, even though it kind of overshot the truth, it's still improvement because we got smaller errors. But then look at all of the rest parameters. HMF2 didn't improve. The top side thickness even got worse. Bottom side thickness got worse. NME got worse. So the conclusion here is that Okay, let's focus only on NMF2 because that's the only parameter that we can actually improve with the ground-based GPS data. And let's forget all of the other parameters. But we don't just forget them. We use cosmic 2 radio occultation to correct all of the other parameters. Since Anchor uses parameterized ionospheric data assimilation method, we can actually analytically find by how much do we need to change our NMF2 for the ground-based TAC measurements to match the observations. So this picture illustrates it. With the black line, we have the expected slant tag from just one ground-based station that communicates with several different GPS satellites. And the red line shows the observed S-tag. Then we find this difference between observed and expected S-tag, and then we convert it into by how much NMF2 should change to match that difference. And so the next plot shows the NMF2, and the corrected one is the red one, and it's very close to the blue one, which is the truth. So we only extract the NMF2 parameter from the ground-based S-tag data, and then we ingest it in the same sense with all of the other points, but only for the NMF2 values. So again, here we start with the background, and I'm showing the percent difference with the truth on the right, and the analysis has way smaller percent difference from the truth. We are improving, which is good. So then we evaluated the influence of different data sets for Anchor, and that's again synthetic data. So here again, root mean square arrows. We start with the black line, which is our pi-RI model. If we add only ionozones, we are improving basically from 0.3 to 0.2 in terms of root mean square arrows. And then if we add cosmic 2, just the cosmic 2, it will give us 11% of decrease in RMSE. And if we add S-tag, it gives us 41.6% decrease, which is a lot. Well, that's because it's a global coverage, right? With cosmic 2, we have only equatorial coverage. But anyways, when we combine all of the data types, we can get up to 46% reduction in the arrows. We started very rigorous validation of Anchor. We conducted one study where we used incoherent scatter radar data to do the validation. So we looked at 4 different radars: Hikamarka, Milston Hill, Arecibo, Pfizer. We found 4 events with different solar activity where at least 2 radars were operational. And we are not ingesting the incoherent scatter radar now to assimilation, but we compare it to the results of the assimilation. Here is a result from Arecibo, which has, well, of course, the best high resolution data. pi-RI background is shown with blue, ISR measurements with red, and Anchor, as you can see, is very well on top of the data. If we now look at all of the events, this panel on the right shows basically when the bar is green and negative, it means good. It means decrease in the root mean square arrows. So for the NMF2, for HMF2, we got as much as 75% reduction of arrows, which is amazing. For the so the thickness of the bottom side of F2 layer is the most complicated parameter because it's constantly getting kind of messed up with the F1 layer. So sometimes the ionogram can confuse F1 layer with F2 layer, and that affects the thickness. So there are those complications. That's why sometimes we have those red bars, which is not ideal, but we will be working on it. And for the top side, we do get the green bars. And this top side is only due to the cosmic 2 data, because GPS data in our assimilation does not affect the top side. Ionozones don't have a top side. So these green bars in the last panel, those are all due to cosmic 2. We compared our results with IRTAM, or we used PyIRTAM, which is also an extension of PyIRI software. And so these plots show green points are PyIRTAM in comparison to ISR data, and yellow are Anchor in comparison to ISR data. And the conclusion is PyIRTAM and Anchor are very similar to one another. But Anchor includes Cosmic 2 and GPS data, but PyIRTAM does not include that. The results of the study were submitted to Radio Science, and those are the work of my summer intern, Andrew Pepper. Did a great job. That's all. I want to advertise some community available tools. Again, on GitHub, you can find PyIRI, you can find PyIRTAM. Anchor is not publicly available software, but you can always contact me if you want to use it for scientific investigations or to collaborate together. Thank you so much for your attention.
Yeah. All right, I think we have plenty of time for questions. So if you have one, please come up to the microphone.
Very interesting work. Yeah, I want to say it's a comment I made similar to before, which is this approach really makes sense due to the lack of a physics-based model that can kind of fill in where you don't have data. I think that's what happens in the atmosphere. So I think it's really a significant result. What is PyIRTAM? I'm sorry, I missed that at the very end.
So PyIRTAM is an extension of PyIRI code. So IRTAM is kind of set of coefficients that are being updated every 15 minutes. They use a gyro ionizone database to produce those corrections to IRI model.
So those are real time?
Yes, real time, but you have to have license for the real time, but the 1-day latency coefficients are freely available.
Okay, so it should be superior to IRI because it's updated with recent.
Absolutely, yes. Okay. At NRL, we consider it basically a gold standard for ionosphere. And about the physics, so Anchor currently is coupled also to SEMI-3 fully physics-based model. And so we used PyIRI only for the development purpose to get the background very, very fast. But currently Anchor is working with SEMI-3. So, and meaning that the forecast and the nowcast, we actually update the physics of the ionosphere with data assimilation.
Hi, thanks, Victoria. That was really great. I'm wondering if you have any thoughts about how Anchor could work or be used, or whether it would be effective for topside ionosphere, or at least F region and above, just for specifying sort of LEO S-Tech for POD antennas.
How Anchor can be used, or how it's doing?
Well, have you looked at that?
Yes. Okay, so let me that. Okay, so this picture. The last panel shows the topside parameter, thickness of the topside. And yeah, as I mentioned, we have improvement there only due to the Cosmic 2 data. And well, if we include any other commercial data set, that would be a way better improvement because, well, here it's only equatorial region. Yep. Yeah, so that's why we're very grateful for Cosmic data.
I think we're out of time, correct? Okay, sorry, thank you. Please find Victoria during the break. Let's welcome our next speaker is Charles Lin from National Cheng Kung University.